Welcome to my Key Study Circle channel. In this video, we shall see how to perform the stress analysis of a cantilever beam using the ANSYS APDL software. Moving on to the problem statement. An aircraft wing of 3.5 meter span acts as a cantilever beam. The three gas turbines located at a distance of 1 meter, 2 meter and 3.5 meter from the fixed end exerts a transverse load of 20 kilonewton, 20 kilonewton and 10 kilonewton respectively. Draw the bending moment diagram and the shear force diagram. Also compute the bending stress and the deflections induced in the beam using the ANSYS APDL. The cross-sectional area of the wing is 0.12 meters into 0.2 meters. The Young's modulus is 200 GPa and the Poisson's ratio is zero point 0.3. So here you can see a cantilever beam. So the air wing is assumed to be a cantilever beam. One end is fixed to the air body, and there are totally three turbines located at C, D, and B locations as illustrated in the figure. So each turbine is exerting its weight as a transverse load of magnitudes 20 kilonewton, 20 kilonewton, and 10 kilonewton respectively. So we need to compute the shear forces and the shear force diagram, the bending moments followed by the bending moment diagram, the deflection and the bending stress that is induced in the beam. So before we start with the ANSYS APDL, let us try to calculate the parameters using the strength of material approach. First is the calculation of the reaction force. So since the transverse loads are acting downwards, so they can be treated as negative and upwards as positive. So here let us assume that there is a reaction force at the support, and since it is a cantilever beam, we have got the support only at one end of the beam, and let the reaction force at that end A be given as R of A. Considering the sum of forces in the y direction to be equal to 0, we have got the summation of all the forces in the y direction, that is acting downwards, to be negative, and the reaction force will be in the direction opposite to the applied load, so it is positive. So the magnitude of the reaction force will be equal to 50 kilonewtons, followed by the shear forces and the shear force diagram. So we do know that the reaction force at the end support is 50 kilonewton. So considering the portion dB of the beam, so let us start from this particular end of the beam, that is dB portion. So in this portion, we have got at the point B a load of 10 kilonewton acting. So we can just see that the shear force is having a magnitude of minus 10 kilonewtons, which is a constant until the point D. So at D, we have got a load of minus 20 kilonewton. So including the effect of this particular load, 10 kilonewtons. So the magnitude now increases to minus 30 kilonewtons as illustrated here. Next, coming to the portion CD of the beam. So we do know that it is having the effect of these two forces, that is minus 30 kilonewton, and also this particular load, which is of magnitude 20 kilonewton. So it is minus 50 kilonewton at the point C. And this entire minus 50 kilonewton is distributed throughout the end point A. And in the portion AC, there are no other point loads acting. So this effect of minus 50 kilonewtons is seen till the end point A, which is also the reaction force at the support A. So this is the shear force at the end A. So we have got the shear forces at the different locations, at A to be minus 50 kilonewtons, at point C to be equal to minus 50 kilonewtons again, and at point D to be equal to minus 30, and at point B equal to minus 10. Moving on to the bending moment and the bending moment diagram. So considering the portion dB of the beam, so there is a load of 10 kilonewtons which is acting, and this 10 kilonewtons, we can just assume that at B, the distance, the total distance x is equal to 0, and the bending moment m is also equal to 0. So this will start from the endpoint D, that is to be 0, at D is equal to x point, okay, that is x is equal to 1.5 meters. We have got the bending moment formula as the load into the perpendicular distance. So it is minus of 10 into 1.5, which is equal to minus 15 kilonewton meter. That is the magnitude of the bending moment at the point D. Next, coming to the portion CD. So we have got the forces of at B and D. So from the free end, this is the force. So considering the effect of 20 and 10 kilonewtons, and at a distance of x is equal to 1.5 meters, we have got the bending moment at the portion CD to be equal to minus 15 kilonewtons again, that is at the point D. Then adding on to this perpendicular distance, that is 1.5 plus 1 meters, we have got x is equal to 2.5 meters now. And the magnitude of the load is, say, 30. So it is 45 kilonewton meters at the point C, considering the effect of these two forces. Next is considering the portion AC. So measuring from the free end, that is x from the free end is equal to 1 meters. So this is the moment calculation. So that is minus of 10 into x plus 20 into x minus of 1.5 and plus 20 into x minus of 2.5. So that is the total distance. So upon substitution, we get it is minus of 50x into plus 80. So x is equal to 2.5 meters. That is uh, at this point. So 1.5 plus 1. So this is the perpendicular distance. So we get the magnitude of the bending moment to be equal to minus of 45 kilonewton meters at the point C. Okay, so it transcends to total length of the beam, which is equal to 3.5 meters, and the bending moment now is equal to minus of 95 kilonewton per meter. So this is the magnitude of the bending moment at the salient points A, C, D, and B as shown in the figure. So now we have solved the problem statement using the strength of material approach. We have computed the values of the reaction forces, shear force, and also the bending moment. So now it's time for us to understand how the stress analysis could be performed using the ANSYS APDL. So we'll begin with selecting the preferences to be structural. Click OK. Go for preprocessor. Let us select the element type. Click on add. Click add again and select a beam element. Let it be a 2 node 188 element. Click OK. Let us set the polynomial equation to be a cubic type. So for that, go for options and select the element behavior, that is K3. Change it from linear form to cubic form. Click OK. Click close. So we have selected the 2 noded beam 188 element. Next, we'll go for the material properties. Go for the material models. Assign the structural, linear, elastic, isotropic. Assign the Young's modulus of 200 E3 MPa. And next, the Poisson's ratio of zero point 0.3. Click OK and close the dialog box. Next, we'll go for sections. So we need to assign the cross-sectional area for the beam element. So go for beam, select common sections. So let the ID be number 1. So here you can just give it as cantilever beam. The name is cantilever. And the cross-sectional area you can just select from the multiple options here. So it is a solid rectangular cross-sectional area. So you can just select this. So it is asking the parameters of B and H, that is the width and the depth of the beam. So I can just feed the values of 0.12 meters as the width and then zero point 0.2 meters as the height or the depth of the beam. Click OK. So now we have defined the cross-sectional area. So the moment of inertia and everything will be calculated by default in the system. So now let us go for modeling, create the nodes in the active CS. So the first node is always the origin. So enter the node number as 1 and click apply. Now the node number 2 is at a distance of 1 meter from the origin. Click apply. So we'll use the nodes wherever the loads are acting. So at node 3, which is at a distance of say 2 meters from the origin, click apply again. Next is the node 4, which is totally at a distance of 4.5 meters from the origin. It is at a distance of 4.5 meters. We can just check it with the problem statement. So the node 1 is at 0. Next is the node 2, which is at a distance of 1 meters, and the node 3, which is at a distance of 2 meters. So that is 1 plus 1, which is equal to 2. And next is the distance of 3.5 meters. So we'll just get back to the node numbers and enter the node number. So this is the active node, that is the node number 4 now, which is at a distance of 3.5 meters from the origin. Click OK. So we have got totally 4 nodes. One is the support, and the 3 nodes representing where the loads are acting. So now let us create the elements auto numbered through nodes. Pick 1, 2, click apply. Pick 2 and 3, click apply. Pick 3 and 4 nodes and click apply. So now we have defined the FE model through the nodes. So now let us go for applying the loads and the boundary conditions. So go to the loads, select define loads, apply structural displacement on nodes. So select the first node. Since it is a fixed support, all the degrees of freedoms is constrained here. So select all DOF and enter the displacement value to be equal to 0. So you can just see that the node 1 is constrained completely. So now we need to apply the loads. So go for structural, select force or moment on the nodes. At node 2, there is a load of minus 20 kilonewton which is acting. So minus of 20, click apply. And at node 3, click OK. So again minus 20, click apply. Select the node 4, click OK. Change the magnitude to minus 10 kilonewtons, click OK. So we have defined the FE model, that is node 1, all the degrees of freedoms are constrained. At node 2, 3 and 4, so we have got all the loads that is defined. So now it is time for us to solve the FE model. So go for solution, click solve, and select the load step, current load step, click OK. So the solution is done appears, click close. Now go for general post processor, select list results, select the nodal solutions, select the degrees of freedom solution, displacement vector sum, and click OK. So you get to calculate the deflection. So the deflection of the displacement of the beam along the y direction is computed here. So at each node, the corresponding values of the displacement is given. You can record this. Next, let us go for recording the reaction solution. So in the same list results, select reaction solution. All items, click OK. So obviously there is the load acting in the y direction, and the reaction force is always at the node where the support is provided. So it is at node 1. So Fy is 50. So this is the value of the reaction force, and these are the moments at x, y, and the z direction for the node 1. So record the values and click close. So now let us see how the values of the bending stress, the shear force, and the bending moment could be computed. So now let us go for the prompt bar and enter SAT, that is set, and click enter. So now let us define the table. So go for element table, select define table, click add, and enter for the shear force in the ith node SFI by sequence number SMISC, so followed by the number 3. For the shear force, it is 6. So click apply. Similarly, the shear force for the jth node by sequence number SMISC 19. Click apply. Now let us define the bending moment. So BM, that is the bending moment in the ith node, sequence number 3. Click apply. Similarly, the bending moment at the jth node by sequence number, select SMISC, and the number is 16. So I'll be detailing why we are using only these specific numbers. So click OK. So now we have defined the shear force and the bending moment using the components 6, 19, 3, and 16 for the I and the jth node respectively. Click close. Go for plot results, select contour plot, select the line element results. So map the I and the jth node for the shear force. So click OK. So you can just see the shear force diagram and the magnitude of the shear force. So this is minus 50. So this is minus 14.44, so almost close to the values that we've got in the theoretical solutions. Next, we'll go for computing the bending moment. So go for line element results again. Select BMI and BMJ and click OK. So this is what is the bending moment values. So the minimum value is minus of 95 kilonewton meter as we got in the theoretical calculations. So these are the values that we get. So this is the deformed and the undeformed shape of the beam. So now you can go for plot results, select deformed shape, deformed plus undeformed. So this is the line diagram. Go for plot controls, select style, size and shape, and switch on the display of element. Click OK. So this is the 3D view of the beam which is deflected. So you can just see this is the original position and this is the position of the beam due to the loads, the transverse loads which is acting on its surface. So now let us compute the values of the bending stress. So for that again, go for element table, define table, click add. So let me call it as bending stress at the ith node by sequence number SMIC 32, and then click apply BSJ. So select by sequence number and 37. Click OK. So go for plot results, contour plot, line element results. So select the components of the bending stress. So that is bending stress I and bending stress J. Undeformed shape, click OK. So keep it in the front view so you get to see the values of the stress, that is the bending stress that is induced in the beam due to the transverse load which is acting on its surface. So now let us see how to have this plots in the multiple window layout. So go for plot controls, select multi window layout, and let me go for selecting three, that is two at the top and one at the bottom, or one at the top and two at the bottom. Click OK. So now go for plot controls again, select multi window layout. Okay, we have already defined the layout. Let us select the multi plot controls. For the window 1, entity plots, click OK. Go for line element results, click OK. So let us keep the bending moment diagram in the first window. Click OK, right click and select replot. So you get to see the bending moment plot. Go for plot controls, select multi-plot controls again. So window 2 is this, you can see the number 2. So entity plots, click OK. Select line element results, click OK. And change this to the shear force diagram, SFI and SFJ. Undeformed shape, click OK. Right click and tell replot. So you get to see the shear force diagram. And here we can have the deflection of the beam. So go for plot controls, select the multi-plot controls. So we can have the bending stress. So we can go for click OK. Line element results, click OK again. So match BSI and then BSJ, click OK. Right click until replot. Okay, it was in the window 2. So let us change this to window 3 now. Plot controls, window 3, entity plots, click OK. Line element results, click OK. So we need to have the shear force diagram. So SFI, SFJ, click OK. Right click until replot. So this is the shear force plot. So in a single window, we have divided it into three layouts, and we have got the bending moment plot, we have got the stress plot, and we have also got the shear force plot for the cantilever beam, which is given in the problem statement. So you can just go for plot controls and select the right metafile option. So invert white or black, and you can just see that it is going to download as a file. So let us just rename it into plots for cantilever beam, and let us just save this. Now you can just check it in the folder wherever it is saved, so it will be in the format like this. So you can just see that in a white background the plots have been saved, so you can just keep this ready for the print. And if you need to include any specific text in this particular window which has to be a part of the print, then just go for file and then select change title, and here I can just type it as analysis of cantilever beam and click OK. Right click until replot. So you get to see the title that has been given here. So this could be used to put up your names or any other data in the worksheet. So you can just check it out. So go for plot controls, select write meta file, invert white or black. Let me rewrite the file, click save. You can just see that the content is appearing in the sheet as you can see here. So you can just change this to a JPEG file. So just go for file and click save as a image file in the JPEG format, and this will be saved as a file in the JPEG format. So with this, we complete the problem statement wherein we have computed the values of the reaction forces, the deflection, and also the shear stress, the shear force, the bending moments, and also the bending stress that is induced in the beam. Thank you all for watching.